So it's very nice to have our in-house ICTS in-house meeting again, which we could not have in previous years because of pandemic. So I thank the organizers for doing this. So today I'll talk about entropy growth in free expansion of ideal gas. This is a very simple example that probably all of you have seen. So this is a work done in collaboration with Subhadeep Chakravarti. He was a postdoc at ICTS, now in Germany, Abhishek, and Sally Goldstein and Joel Lewis from Rutgers University. I think this is not the updated slides. So anyway, let's continue. Okay, so so the reference is actually wrong. I had sent an updated slides, but yeah, somehow it didn't come here. Okay, so the second law provides an arrow of time, and it quantifies irreversibility that we all know, which we see in evolution of macroscopic observables, macroscopic quantities. And the big question and the broad question is, how does this irreversibility emerge from microscopic reversible Newtonian dynamics of many particle systems, as we see in expansion of gas, which is in a isolated in a box which is isolated from the rest of the environment. Okay, so there are lots of explanations. There are a lot of people have thought about this question. And Boltzmanns gave an interesting and simple explanation, which is the following: that the observed irreversibility is the typical macroscopic behavior given appropriate initial condition, which is typical initial conditions, and that becomes a certainty when there are very large number of degrees of freedom. And this is actually very nicely summarized in this quote by Joel Lewis. He says that this is the only factor, the time factor, that you have very large number of degrees of freedom, which actually permits a certain certain macroscopic evolution for typical individual realizations, and the precise assumptions that usually people make is ergodicity, mixing, and equal priority probability, which are not required to be strictly satisfied. Okay, so Boltzmann tried to describe this irreversible behavior by growth of an entropy function that he defined for a single microstate of a macroscopic system, not for an ensemble of states that usually we do in the statistical mechanics. And he provided a clear prescription for the construction of this entropy function. And in his construction, one can actually define this entropy even for a system out of equilibrium at any time. And for a generic system, he argued that it will typically increase and finally saturate to the equilibrium value. So let me elaborate on Boltzmann's definition of entropy. How did he do that? So he associated an entropy to each microstate X through a macrostate. It realizes upon coarse graining. So when you define a macrostate, from a microstate we introduce some coarse graining. And so for a given microstate, you can actually, once you have decided your coarse graining, you can get a value for the macrostate. And then you assign the entropy to this microstate by taking a log of the volume, which actually counts the number of phase space points which correspond to the same value of the macroscopic variable that is obtained from this microstate. Okay. So, for example, let us consider this example, which is a gas field of a box field of gas. So the microstates are basically positions and momenta of these particles, and one macrostate is, let's say, the number of particles on the left half of the box. So obviously, this is a function of the microstate. Given a microstate, you can actually count the number of particles on the left half of the box, and this is a function of the microstate, but it's of course a many-to-one map. And once you have the value for the macro variable, then you can easily realize that there could be many microstates configuration which will have the same value. So once you have a microstate, you do a coarse graining, you get the macrostate value, and then find out the number of microstates corresponding to this macrostate value that is given by this, which is represented by this volume, and take a log of that and call that as an entropy of the microstate X. That's how Boltzmann defined the microstate. And by this definition, it actually allows to partition the phase space of the isolated system in the following way. So let's so consider an isolated system which is characterized by some let's say energy, momentum, and all sorts of other conserved variables. But let's consider only energy, for example. So you have microstates, and you can construct a macrostate from the microstate given once you have decided a coarse graining description. And you can see that, you can easily see that, as I said, there are many microstates which looks macroscopically same. That means there are different microstates for which the macro variable are same, value are same. And using this property, you can actually group all possible collections of microstates, such that which has same value for the macro variable. And that way you can actually have a partition of the full phase space into equivalence classes according to the value of the macro variable. And as the phase space point, so the dynamics is Hamiltonian or Newtonian. So you start from let's say microstate, which is a point in the phase space. As it moves, it moves within this full phase space. It typically explores new macro regions. And of course, for a typical evolution, it is easy to imagine that it will enter region partitions with larger and larger volumes. And there is another interesting fact is that for almost most macroscopic system, there exists one macroscopic state which actually contains almost all the volume of the full phase space. And that state is called, macrostate is called the equilibrium state. So typical initial conditions actually finally end up in this state and stay there for a long time, and that you can ascribe to be an equilibrium. And if you define entropy that the way I have defined it, you can easily see that it will typically increase and approach to this equilibrium value. That's how this was Boltzmann's explanation. So in this work we tried to demonstrate some of these ideas through the simple pedagogical example of free expansion of an ideal gas in one dimension. So we have n point particles of unit mass inside a box of size L, and initially they are all on the left half of the box, and they interact via elastic collisions, and in between collisions they move ballistically. So the microstate, and also they have elastic collisions as well as with the walls. So the microstates are Xi's and Pi's, and we considered initial condition. We consider two initial conditions. One is one microstate chosen from the thermal state with the gas combined in the left half of the box, and another is thermal initial condition, which is you choose the initial conditions from thermal state and you average over the initial conditions. Evolution is Newtonian. And the macroscopic evolution in this case, as you expect that the macroscopic evolution is that all the particles will try to fill the box. So the macroscopic evolution is gas filling the box. And question is how to quantify irreversibility through an entropy function that is defined for a single microstate, not an ensemble at every time. So for that thing, we need to define macrostates. So we make two choices of the macrostates. One is empirical single particle distribution. Another is density of first three conserved fields. So let me elaborate on these two choices. So first one is the single particle distribution function. How do we define? So this is the single particle phase space X and V or the momentum. And we divide this phase space into boxes of some scale, coarse-graining scale mu, and find out the fraction of particles per unit volume of so the number of particles per unit volume of this. Let's call this F alpha. Alpha is denotes the alpha box. And in the n going to infinite limit, you can find out for given set of values of F alpha what is the entropy. You can find out the number of such microscopic configuration which give the given set of values for alpha. And you can do this calculation simply. These are classical particles, and it will turn out to be this, which is not very difficult to find out. The second choice is here we kind of divide the space, not the phase space, the physical space, into some cells of size L, and consider the number of particles in the cells, total momentum, and the energy. These are like the macroscopic variables that you consider usually in hydrodynamic descriptions. So this is the particle density, and this is in the internal energy density in this box. And given these densities, particle density, internal energy densities, you can count the number of microstates that actually are associated consistent with this value of internal energy density and the particle density, which is the usual calculation that you do. And then you can add all the contribution for all the boxes, and that gives you the entropy of the full system.
You have 5 more minutes.
Yeah, I'll finish within that. So we observe the evolution of these macroscopic observables and as well as the associated entropies for this. So this is the scatter diagram, phase space diagram of the empirical particle distribution. Each points basically a particle. So initially all the particles are in the left half of the box. The box size is 4, and the velocities are chosen from a thermal initial condition, but this is a single initial condition. Now, once it evolves, this phase space distribution scatter plot actually changes, and it fills up the full phase space. And if you look at the distributions evolutions are looking like this. Initially, they are in the left half of the box, and then later they fills the full box, and you see the distribution. Here I show distributions obtained from 2 initial conditions. One is from single typical initial condition, which is the dashed line. Another is the same thing averaged over thermal initial conditions, and we see that at each time they actually agreeing very well, matching very well with each other, which means that this for single typical initial condition also the evolution is typical, and the corresponding entropy increases and reaches a final value. So the final change per particle is log 2. Here I am plotting entropy per particle. Symbols are from single typical initial conditions. Solid lines are over thermal initial conditions, and they agree with each other. And we see that this growth actually depends on the coarse graining scale. As the coarse graining scale is decreased, the rate of entropy production is decreased. So because this is a non-interacting system, so as you decrease the coarse graining scale, you should expect that it should decrease. However, there are some interesting oscillations which we can understand analytically, and also there is some collapse. If you do the scaling of the time properly, you can collapse the full function. So that means if you can actually scale your time and look at this evolution in that scale time, and you can always see entropy growth, even in the coarse graining size going to 0 limit. This is the macrostate choice 2, where you consider density, velocity, and the temperature. And once again, we look at the evolutions, and they compare with the ensemble average and the single initial configuration, and they again agree with each other, which shows typical evolution. And this typicality emerges in the thermodynamic limit. This plot actually shows that as we increase n, the density profile actually matches with the thermal average very nicely. And the corresponding entropy for the macrostate choice is also again increasing, and the final increase is again log 2 per particle. However, in this case, we find that it even with the as the coarse graining scale goes to 0, this entropy function actually converges to a single curve, and it is monotonic. And we also have some understanding of the entropy growth in this case. So I am not going into that details. So in conclusion, we have studied free expansion of ideal gas in one dimension to demonstrate Boltzmann's idea of entropy and the irreversibility through two choices of macrostates, so F and U, and both demonstrate some kind of thermalization, and in each case the final change in entropy is log 2 per particle. However, the growth depends on the coarse graining on the choices of the macroscopic variable. And there are some important points is that in this case, of course, this is a non-interacting particle system. So you do not expect to have ergodicity, chaos, and of course non-integrability, even though you can describe irreversibility and entropy increase in this case. And the essential factors are that you start with a low entropy initial condition, and the initial conditions are typical, and you have large number of degrees of freedom, and you have coarse graining. These are the important factors to kind of demonstrate irreversibility and entropy increase. Okay, so there are further interesting questions how to demonstrate these things in the context of interacting gases or quantum systems, which we are currently studying. So thank you for your attention.
Thank you for your talk. Now we'll have a couple of questions.
Thanks, Anupam. So you can, in this case, study the approach to equilibrium also. So you can read off hydrodynamic parameters.
In the sense of what kind of parameters you are talking about?
Like the transport coefficients.
No, the transport coefficients, I don't think from this you can actually get just from this entropy evolution curve. If you have those, then that actually gives you that the entropy should increase. But just from this curve, I don't think you'll be able to
you
get.
Cannot extract from the rate.
For example, in the
Navier-Stokes
Navier-Stokes equation, if you have those Navier-Stokes terms and the Fourier terms, I think the entropy increase should depend on all these parameters, right? But just from this curve,
I thought from the single particle phase space, this thing you can, I mean, but I guess you don't have interactions really.
Yeah, in this
so,
case, we don't have. No, in this case, I think the entropy increase is because of the coarse graining. So you actually have left out many of the information. So your, yeah.
So I was just wondering what sets the time scale for the.
In this case, we have understood the time scale pretty well. In this case, even the oscillations and these time scales, these are actually dependent on the coarse grain scale.
Oh.
And actually, if you so there is a you see that there is a period. That period is given by the delta V that we use the coarse graining. So the explanation is the following. So suppose you have an initial configuration in which you have a particle which, let's say, two particles with velocities very close to each other within delta V, and they will again appear in the same grid in the position space after integer multiples of 1 over delta V, right? And that's why you have these oscillations, and these actually also gives you this time scale also comes from the coarse graining scale. First one is 1 over delta V actually.
I see.
But the other one, I think it's also dependent on this one. Yeah. This one we didn't think about what is the time scale to. Yeah, we didn't think about. We didn't. Yeah. You have any comment? This I didn't think.
For if it is an interacting system, then of course the entropy production depends on the transport coefficient.
Yes.
But in this case, I mean.
Yeah. So, but that's why I was wondering what sets the scale.
So this is, I mean, described by generalized hydrodynamics, and then yeah, I'm not sure.
Yeah.
Yeah, we haven't thought actually.
Any further questions? Okay, so let's thanks Professor Anupam for his interesting talk.